My name is Andrew Jackson. I'm a geologist with Global Resource Investments, and I'm responsible for technical evaluations of the mineral companies and their properties that Global invests in. I put together this Ore Deposits 101 series of talks to help non-technical people understand ore deposits. The talks highlight some of the features of the main deposit types that investors in the resource sector may come across, and provide an introduction to the jargon that you will find in press releases put out by exploration and mining companies. This talk is the fourth in the Ore Deposits 101 series, and it covers one of my favorite groups of ore deposits, the so-called mesothermal or Greenstone shear zone hosted gold deposits. You may also hear these deposits referred to as orogenic gold deposits, although I don't particularly like the term, as most gold deposits are related to orogenesis, which renders the name pretty meaningless. To paraphrase property realtors, the three most important controls in the formation of this group of ore deposits are structure, structure, and structure. And this is probably not much of an exaggeration. Keep this in mind as we go through their genesis. As in other talks in the Ore Deposits 101 series, I'll show why this group of deposits is important to us, how the deposits form, how we explore for them, and how we mine them. You'll remember from earlier talks that nature concentrates metals by a process of partially melting crustal rocks at depth, letting the melt rise through the crust and cool, dumping the valueless materials such as feldspars on the way, and concentrating the useful materials and metals in the remaining magma or hydrothermal fluid. Cool, dump the dull stuff, skim off the useful metals. Mesothermal gold deposits form halfway up through the rise of the melt from the deep crust to the surface, usually at a depth of less than 10 kilometers, but greater than 1 kilometer. Temperatures at these depths are generally somewhere between 450 degrees and 250 degrees Celsius. So where do we start? The term mesothermal veins is really a SAC term, referring simply to the depth of formation. It pays little attention to the origin of the mineralizing fluids. This group of deposits formed throughout the Earth's long history, all the way from the very earliest Archean, say 3.4 billion years ago, right up until today. However, the remainder of this talk focuses on the Archean and lower Proterozoic age deposits. As I mentioned, these deposits go by several names, depending on who you talk to. Greenstone gold, Archean shear zone hosted gold deposits, shear zone hosted gold, or orogenic gold deposits. They all refer to pretty much the same sort of deposit. Well-known examples of this group of deposits include the Kalgoorlie Superpit in Western Australia, Campbell Red Lake and Giant Yellowknife deposits in Canada, Ashanti and Obuasi in Ghana, Las Cristinas in Venezuela. Although somewhat unusual in its characteristics, the Hemlo deposit in Canada can also be included in this group. The image is of a 3D model of the St Ives mine near Kalgoorlie in Western Australia. The brown shape at the top is a section through the open pit. The other colours represent the mineralized shears. Displaying multiple shears are typical of thrust duplex structures that form during compression of host rocks, and these often act as hosts to mineralized veins. So how significant are these greenstone belt shear zone hosted gold deposits in the grand scheme of things? This graph shows the gold grades of various types of deposit being mined in Canada. Greenstone shear zone hosted gold deposits are in yellow, and you can see that they tend to grade between say 7 and 10 grams per ton, well above the gold grade of most other deposit types. In a world where grade is king, this is important.
So much for grade. What about the volume of gold produced? Here again in yellow you can see how in Canada the vast majority of gold mined each year is derived from Greenstone belt shear zone hosted gold deposits. This is less striking if we take worldwide production figures, in which Witwatersrand gold and Carlin type deposits produce more significant proportions. But even globally, shear zone hosted deposits are major contributors to annual gold production. As I mentioned, mesothermal veins have formed from the earliest period of the Earth's history right up until today. However, the majority of the Greenstone belt gold deposits formed in two main pulses, at the end of the Archean and in the early Proterozoic, i.e. around 2.7 billion years ago and 2.1 billion years ago. Although this sounds a very long time ago, these deposits formed only about halfway through the Earth's history, and this diagram puts it into perspective. The Earth originally formed about 4.6 billion years ago, and dinosaurs evolved only just 150 million years ago. And humans barely register on this scale. Not all the Earth's crust that was in existence at the time of formation of these deposits is still visible today. Some has been eroded, and other parts of it are now obscured by thick sequences of younger sediments and volcanic rocks. The figure shows in purple where the remaining portions of these old cratons, as the old crust is called, exist today, although major parts of this extent are obscured by thin cover rocks. But when you strip away the cover, as has happened in a number of areas, you can see that this early crust looks very similar wherever in the world you see it. This is a satellite view of the typical Pilbara craton in Western Australia, and it gives a good idea of the geological architecture of this old crust. The image covers an area of 140 kilometers by 10 kilometers. The area to the south, coloured in yellow, is the young cover, obscuring the underlying Archean craton. The darker greenish coloured areas are the old volcanics and sediments, and you can see why they're referred to as greenstone belts. The pale buff-coloured areas are granite plutons, and those have risen up and shouldered aside the greenish volcanic rocks. The speckled unit in the southeast is considered to be part of the Greenstone belt, but comprises pebbly conglomerates that were deposited as the rising granite plutons were eroded. Now you can take almost any part of the old cratons worldwide, and they'll have similar rock types with the same order of formation and the same style of deformation. And I'll come back to this later in the talk to show you how the crust developed and its influence on the gold mineralization. Let's turn to the mineralizing process now. All hydrothermal deposits need three things. They need a source of fluids and metal. They need a channelway through the crust to transport the metal upwards from the source area, and they need a trap where the physical conditions change to cause the metal to drop out of the fluid and form the ore deposit. We'll start with the source. The source for the gold itself appears to be in a gold-rich enriched layer in the deepest portion of the crust, about 20 to 30 kilometers below surface. This gold-enriched source area seems to have been particularly well developed in the Archean crust. Later form crust is less enriched. The partial melting of this crust usually triggered by folding and thrusting of the crust, which thickens and pushes the lower portions deeper into the underlying mantle where they melt. As described in my first talk in the Ore Deposits 101 series, the gold is concentrated into the melt portion of the partially melted rocks. Analysis of oxygen isotopes in the hydrothermal fluids has shown that the water that comes out of that melt is derived from metamorphism and melting of the crust rather than from any deeply penetrating groundwater. Many minerals, when heated under pressure, break down to form different minerals and give off water in the process. A channelway is the second requirement for a hydrothermal deposit. This is needed to get the gold-bearing fluid from the deepest part of the crust up to where something triggers the gold deposition from the fluid. How does it travel? Well, gold, as you know, is barely soluble in pure water, so it needs to combine with other elements to become soluble. The most common form for gold to travel in is with chlorine as a chloride complex, or with sulfur as a thiocomplex. In the case of these shear zone hosted gold deposits, the gold is transported dominantly as a thiocomplex with the sulfur. As a thiocomplex, the gold can be carried at a concentration of as much as 10 parts per million. Although the fluid starts off at higher temperatures, studies show that by the time the gold begins to drop out of solution, the fluids are at a temperature of between 300 degrees and 500 degrees Celsius. In spite of these high temperatures, the fluids are usually not boiling because of the high confining pressures at those depths. The hot fluids tend to rise, and they'll take the easiest route they can find up towards the surface. And the bigger the structure, the more fluid it can carry. And because we need a lot of fluid to produce a big gold deposit, we need to look to the biggest, deepest tapping structures to provide a fluid channelway. Structure is critical. The biggest, deepest tapping structures are usually thrust faults, which may extend down to the lower crust and provide the main channels for the fluids. This is a seismic section through the crust and upper mantle in northern Ontario, in Canada. The boundary between the two is clearly visible, and you can see that the mantle has few seismic reflectors in it, as it's largely molten. The crust, on the other hand, is about 35 kilometers thick and is much more noisy, and it has a host of reflectors. Clearly visible is a group of thrust faults climbing from the bottom right to the top left. Also visible are 2 or 3 areas of the crust with poor reflectance. These represent where the crust was depressed by the earth thrusting and has undergone partial melting. They are the source areas for the gold-bearing fluids which travelled up those thrust faults towards the surface. And it's really no surprise that Goldcorp's outstanding Red Lake mine, one of the world's highest grade and lowest cost producers, is located on a structure that provided the shortest route to the surface for the fluids. Now we come to the most critical part of the mineralizing process. We're less concerned about where the gold came from or how it traveled there, or where and how. We're more interested in how and where it dropped out of the fluid to form the deposit. There are several ways to get gold to drop out of a thiocomplex solution. You can simply cool the fluid, which will happen naturally as the fluid rises into rocks of progressively lower temperatures, or it mixes with cooler groundwater. But this is not a very effective method. A more effective method is to drop the pressure, which will allow fluids to boil, which causes the gold to drop out of solution. This is an important factor in epithermal deposits, but as I said, in mesothermal veins, they're too deep and too high a pressure for boiling to occur. So a more effective way is to get the gold to deposit in mesothermal veins is by causing the thiocomplex to break down and leaving the gold with no way to continue its ride to the surface. In effect, you're destroying gold's taxi and leaving it stranded by the side of the road. How do we do this? Well, by reducing iron oxides in certain wall rocks, such as banded iron formations or mafic volcanics, and this reaction ties up the sulfur with the iron to produce iron sulfide or pyrite, and leaves you with native gold. However, there is another way, and we're starting to realize probably the most effective way of causing the gold to drop out of the hydrothermal fluid, and that's by changing the EH, or oxidation level of the fluid. Most gold-bearing solutions are moderately oxidized and have a neutral pH, equivalent to the yellow dot on the graph there. The red lines are contours of gold solubility as a thio or bisulfide complex. If you mix the fluid with a reduced groundwater derived from, for example, dewatering shales, then a sudden decrease in EH will cause the solubility of gold to drop to less than 1% of its original value. So when we are looking for a gold trap, we need to consider where the oxygenated mineralizing fluid is likely to meet a source of reduced groundwater. Fluid mixing is the most important cause of EH and pH change. In addition to fluid mixing, for a trap to be effective you need significant rock damage to allow large veins or dense network of smaller veins to form. This can occur in virtually any rock type, but brittle rocks shatter better than plastic or ductile rocks, so mafic volcanics and banded iron formations are more common hosts than ductile shales. In addition, bends or jogs in faults provide a great place for open spaces to form and fluid mixing to occur. So again we see that structure plays a critical part in the formation of the trap for the gold. What do greenstone shear zone hosted deposits look like? Well, they usually comprise one or more steeply dipping quartz and or carbonate rich veins. As you can see in the pictures, these sometimes form swarms of veins or even stockworks of narrow veins. Mineralization is irregularly distributed in the veins, often forming steeply plunging high-grade ore shoots. Wall rock alteration is seldom visible to the naked eye for more than a few meters away from the vein margin, although a subtle geochemical halo can be detected with instruments many hundreds of meters away from the vein. The amount of sulfide in the veins varies from almost none up to perhaps 20%. Common sulfides include pyrite and arsenopyrite, with the lesser amounts of chalcopyrite and telluride minerals. Gold is usually fairly finely disseminated, and it's seldom visible to the naked eye. But sometimes it is. And you'll see a lot of press releases put out by juniors give prominence to visible gold, having been observed in drill holes. This is actually not really significant, as it gives little clue as to the grade. It only shows that there's a high nugget effect, i.e. grades are likely to be very variable. You'll also sometimes hear the word refractory applied to gold ores. This usually means that the gold particles are locked up in sulfide grains, and you need to oxidize those sulfide grains in a roaster or autoclave to allow the gold to come into contact with the dissolving cyanide solution. Arsenopyrite is commonly the culprit in a refractory gold ore. In evaluating a shear zone hosted gold deposit, we need to see that there's good grade, that the veins are continuous and not chopped up by later structures, and that they have sufficient width to allow economic mining. So what do we need to form one of these greenstone shear zone hosted gold deposits? Let's take a moment to review what we've covered so far. Firstly, we need an Archean craton to provide the deep source of gold. I believe that even in the slightly younger Proterozoic greenstone belts, the gold is often sourced from underlying Archean crust. Secondly, we need a major tectonic event to thicken the crust and trigger partial melting of the deepest portions, i.e. we need structure. Thirdly, we need a crustal scale fault, or usually a package of thrust faults, to allow the gold-enriched fluids to rise towards the surface. Again, structure. Fourthly, we need a trap to form in the form of structural damage zone, or a location that will allow the gold-bearing fluid to mix with shallow-sourced reduced groundwater. So you can see how structure plays the pivotal role in the development of greenstone belt shear zone hosted gold deposits. And it makes sense for me to talk a little bit more about how greenstone belts form and how this controls the mineralization. I put together a series of cartoons on a long and boring flight to illustrate this process. Obviously this has been generalized and individual greenstone belts vary slightly, with various stages often being aborted or even repeated. But the overall pattern seems to hold true in cratons across the globe, whether Archean or lower Proterozoic. The process starts with some of the earliest continental crust to form on Earth, covered by a proto-ocean. This crust consists of granite-like rocks called tonalites or trondhjemites or granodiorites, and they provide the basement on which the greenstone belts were laid down. As the crust cooled beneath the ocean, it contracted and developed extensional faults. These faults allowed blocks of the basement rocks to collapse and sink to form gravens. Mafic and ultramafic magma from the underlying mantle took advantage of the deep faults and were injected up the faults and onto the sea floor. There they erupted and spread out under the sea in a similar way to what is happening today on the mid-oceanic ridge spreading centers, filling the graben with basalts and komatiites. Komatiites are just ultramafic lavas. As time went on, the magma chambers feeding the volcanoes differentiated to become more intermediate in composition, and the basalts gave way to andesitic lavas. Eventually the magma chambers differentiated to the point where a resulting magma became granitic. Magmas of a granitic composition are far more viscous than the fluid mafic and ultramafic magmas that were originally produced. Instead of quietly flowing onto the seafloor, they started melting the basement and forming large batholithic intrusions. Pulse after pulse of granites enlarged the intrusions until the magma erupted at the surface, building up domes of rhyolite and dacitic lavas and pyroclastics, and these were pushed up above sea level. Throughout this whole process, the original basement faults kept on being reused and remobilized. The felsic volcanic domes continued to grow, and because they were now above sea level, they became subject to erosion by rivers and rain. The products of this erosion collected in the basins between the domes and built up thousands of feet of sediments. The weight of accumulating sediments caused the faults along the margin of the basin to reactivate, and the basins continued sinking, allowing further sediments to accumulate. Not only did the basins sink, but the hot basement material that was forced down escaped the sideways, adding material under the granite domes, further inflating them and steepening the slopes between the rising domes and the sinking basins. Eventually those slopes became too steep for the volcanics and the sediments to resist the pull of gravity, and large parts of the stratigraphy detached along flat, bedding parallel faults and slipped into the basin. You can see exactly the same features forming today along the margins of continents, where the failure often occurs along a weak salt bed or overpressurized shale. In the Archean greenstone belts, failure often occurred along iron formations or ultramafic flows. As these slabs slipped into the basin, they rode on the detachment faults and bulldozed the sediments ahead of them into a series of anticlines and synclines that formed tens of kilometers into the basin. Poorly sorted material from these landslips ended up being deposited into smaller basins or half-grabens developed around the domes. There they formed wedges of conglomerates and greywackies, sandwiched between the granites and the mafic volcanics in the domes, and the grey sediments in the filling the basin. In Canada, you will hear these deposits referred to as Temiskaming-type sediments. Now, up until this time, dominant forces had been vertical tectonics, driven by differences in density between hot, light granitic magmas in the domes and cool, dense mafic and intermediate volcanics filling the basins. This caused the basins to sink and the domes to be pushed up. But at the end of the Archean, this changed, and a worldwide phase of horizontal tectonics, the precursor to the onset of plate tectonics as we know it today, was suddenly initiated. This major phase of horizontal shortening squeezed the domes and caused folding and thrusting, and the final injection of the felsic porphyrian dikes in small intrusions into both, and these were injected into both the domes and newly formed thrust faults. These small, late-stage felsic porphyry intrusions may be the products of the partial melting of the deep crust that was triggered by the onset of that horizontal compression and the resultant crustal thickening. Now, up until this compression, there had been very little significant gold mineralization. But the intrusion of these felsic porphyries always seems to closely precede the main pulse of gold mineralization. The main gold mineralizing event usually took place just after peak metamorphism and deformation. If you remember from earlier in the talk, the best way to get gold to drop out of solution is to drop the EH by mixing the hydrothermal solution with reduced groundwater from a carbon-rich shale. And you can see clearly how this might have happened. As the basins were being squeezed and cooked up by the horizontal shortening, the water from the shales was expelled, taking advantage of newly formed thrust faults. Some of this reduced water was simply expelled onto the sea floor, but some of it was also forced back towards the margins of the domes, where it met the gold-bearing oxidized magmatic fluids. And this occurred around the late felsic intrusions. The most common site for the formation of greenstone shear zone hosted gold deposits is in these major crustal scale fault zones that cut across the craton for hundreds of kilometers, following the junction between the granite and basalt domes and the old sediment-filled basins, very often spatially associated with those late-stage Temiskaming equivalent sedimentary units and the felsic porphyry intrusions. Once all compression ended, erosion took over, and the entire area was planed down to the view that we have today. So what do these major crustal scale faults look like today? Here's a geological map of the Timmins area in Ontario, a typical greenstone type terrain. The map covers about 100 kilometers from east to west. The major controlling structure is the Porcupine-Desta Fault. It separates the granites and basalts of one of these domes to the south from the grey sediments filling the basin to the north. The fault coincides in places with a sliver of the Temiskaming sediments coloured in chocolate brown on this map. The fault also shows up on a magnetic image. You'll remember that I mentioned bends or jogs in the faults as being favourable places for gold traps. The huge Hollinger McIntyre and Dome mines are located in the middle of the biggest bend on the Porcupine-Desta fault zone. So as you can see, magnetic surveys can be very useful exploration tools when looking for bends and structures that are potential hosts to greenstone shear zone hosted gold deposits. What other exploration tools can be used? Well, gravity surveys can be very successful in assisting in mapping the geology of areas where outcrop is particularly poor. It can also indicate where there may be dense mafic material hidden under a thin tectonically emplaced slab of sediments or granites. For example, in this gravity image of the Laverton Greenstone Belt in Western Australia, you can see an area of very dense rocks in red, where the surface mapping of part of this area shows low density sandstones. This indicates that there has to be a thick package of dense mafic and ultramafic volcanics lying underneath the sandstone. Magnetics can also be used to identify magnetite enrichment in the rocks, possibly signifying that the oxidizing fluids have passed through them. Some areas showing this of apparent hydrothermal magnetization are circled in yellow. Obviously, geological mapping is a critical part of any exploration effort, and the identification of the late-stage conglomerates, like those in the photo, can give a further clue as to where the deep tapping structures may occur. Seismic surveys, previously largely restricted to the oil industry, are being increasingly used in greenstone terrains. Because of the small differences in seismic velocity of the various greenstone belt rocks, it used to be thought that seismics wouldn't be practical. However, with improved vibro-seis techniques and computing power to interpret the data, seismics can reveal much of the deep structure of the crust to skilled interpreters. Combining seismic profiles or shooting 3D seismic surveys can allow 3D models of entire greenstone belts to be built, extending down to the base of the crust. This allows explorationists to identify key structures that are likely to have acted as channelways from the partially melting lower crust to potential shallow gold traps. Once areas of potential interest have been identified, the process focuses on these, using various ground exploration techniques. Detailed ground magnetics may be collected to improve the resolution of the earlier regional airborne magnetic surveys. Induced polarization, or IP, may also provide valuable information on the presence of sulfides or silicification that's associated with quartz vein stockworks. With IP, a pulse of current is fed into the ground, and the decay of the wave form, due to sulfides retaining an induced charge, is measured. The picture shows a winter survey underway in British Columbia, and the generator that produces the initial current can be seen in the bottom left. Unfortunately, because of the minute concentrations, gold cannot be detected directly by any geophysical techniques available today. However, geochemistry plays a vital part, both in soil sample surveys and the collection of grav samples during exploration. In addition to assaying for gold directly, so-called pathfinder elements that are associated with the gold, such as silver, arsenic, and tungsten, are also commonly assayed. Here are the results of a soil geochemical survey. Those are the rows of coloured circles, superimposed on a background of geology and magnetics. The soil samples show hotter colours for higher grades, and outline a clear golden soil anomaly in the north-central part of this grid in Tanzania. Inevitably, geophysical and geochemical targets need to be tested by drilling, and this shows the same soil anomaly being drill tested with an RC rig. Some of the issues of exploration in the Third World can be clearly seen, with curious onlookers and livestock arriving to see what's going on. For completeness, I'll finish with a couple of slides illustrating how, once they've been proven to be economic, these mesothermal veins can be physically mined. The traditional method of mining them from underground was using either shrinkage stoping or cut and fill stoping. The cutaway diagram shows shrinkage stoping, where a drift is developed along the ore body, and then another one is developed parallel and used as a transport drift, and that lies in the footwall to the vein. The vein is then progressively blasted upwards, with the miners standing on the pile of blasted ore to drill each successive blast. The broken ore is drawn out from the bottom of the stope to make space for the drillers. The photo shows a view within one of these shrinkage stopes, with the blasted ore forming the floor to the tunnel. However, underground stoping is slow and expensive. If the vein is thick, or there is a dense enough clustering of veins, then open pit mining might be a more economical way to extract that ore. This is particularly the case in shallow oxidized ore, where the grade may have been smeared into the wall rocks. The rock is soft and easily mined, and cheaply processed. Here you can see the giant Kalgoorlie superpit being mined in Western Australia. You can also see where the red oxide ore gives way to the underlying grey primary ore at depth. That then is a quick summary of Greenstone shear zone hosted gold deposits. What are the critical learning points you should walk away with from this talk? Well, Greenstone shear zone hosted gold deposits are an important source of gold, and there are lots of juniors out looking for them. They're vein deposits. They're often high grade, but tend to be low tonnage. Most significant producers are in East Canada, Western Australia, East and West Africa, and Brazil. They have high grade ore shoots in them, and those have a good vertical continuity, but generally have very short strike lengths. About 10 to 20% of deposits are refractory, in other words, difficult to get the ore out of and expensive to treat. And so the three most important things are structure, structure, and structure.